Artificial intelligence is advancing at extraordinary speed, but every new breakthrough depends on physical computing hardware. In this video, we will explore the environmental impact of frequently upgrading the processors, GPUs, servers, and infrastructure used to train AI, and how better hardware lifecycle management can help balance technological progress with environmental responsibility. Artificial intelligence has become a major force across healthcare, finance, manufacturing, logistics, scientific research, business operations, and many other industries. Modern AI analyzes vast amounts of data, identifies patterns, automates complex tasks, and supports decision-making on an unprecedented scale. Although AI appears to exist in software, every system depends on powerful physical infrastructure. Advanced processors, GPUs, AI accelerators, servers, storage, networking equipment, power systems, and cooling technologies work together to train and operate machine learning models. Training sophisticated AI models requires enormous computing resources, with billions of calculations performed across massive datasets. Specialized hardware allows these workloads to be completed far more efficiently than traditional computing systems. As organizations seek faster development, shorter training times, and more advanced capabilities, demand for AI hardware continues to grow. However, frequent upgrades also create a growing environmental challenge, making responsible lifecycle management an essential part of future AI development. AI hardware becomes outdated quickly because machine learning technology advances at an exceptional pace. New models require more processing power, larger memory capacity, faster communication between components, and improved overall performance. For organizations developing AI, faster hardware means shorter training times, more experiments, and quicker innovation. Improvements in energy efficiency also encourage upgrades, particularly in large data centers where even small efficiency gains can significantly reduce operating costs. Software compatibility is another factor. Modern AI frameworks are often optimized for newer processor architectures, leaving older systems functional but less effective for current applications. As a result, AI hardware is frequently replaced long before it physically fails. The challenge is determining when upgrading is truly necessary and when existing systems can continue providing meaningful value through other roles. The environmental impact of AI hardware begins long before equipment enters a data center. Manufacturing advanced processors requires specialized materials, precision fabrication, energy, water, transportation, and highly sophisticated production facilities. A complete AI system also includes servers, circuit boards, memory, storage, networking equipment, power supplies, and cooling infrastructure. Every one of these components carries its own manufacturing footprint, contributing to the overall environmental cost. Frequent hardware replacement increases demand for new equipment, requiring additional resources throughout the global supply chain. While newer systems may improve operational efficiency, organizations should also consider the environmental cost of producing their replacement. Extending the productive life of existing equipment through upgrades, repurposing, or secondary applications allows organizations to maximize the value of resources already invested while reducing unnecessary manufacturing demand. Rapid AI hardware upgrades contribute to a growing stream of electronic waste. Large computing facilities regularly retire processors, GPUs, servers, storage devices, networking equipment, memory modules, and many other components during major infrastructure transitions. Much of this equipment may still function properly, but no longer meet the performance requirements of advanced AI workloads. Without careful evaluation, valuable hardware may be discarded before its practical usefulness has truly ended. Large-scale upgrades can generate substantial amounts of retired equipment in a short period. Organizations that lack structured lifecycle planning may leave hardware in storage indefinitely, making future reuse or recycling more difficult. A better approach evaluates each asset individually, identifying equipment suitable for reuse, repair, repurposing, or responsible recycling once it has genuinely reached the end of its useful life. Upgrading AI hardware often affects far more than processors alone. Modern computing environments are highly interconnected, meaning improvements in one area frequently require changes throughout the surrounding infrastructure. New processors may require updated motherboards, faster networking, expanded memory, improved power distribution, or more advanced cooling systems. As computing performance increases, supporting technologies must often evolve as well. Because of these dependencies, organizations should evaluate entire computing environments rather than focusing on individual devices. Existing infrastructure may still be suitable with targeted upgrades instead of complete replacement. Careful planning helps preserve functional equipment, reduce unnecessary hardware turnover, and ensure only components that have truly reached the end of their useful life are retired. One of the biggest sustainability challenges in AI infrastructure is balancing improved energy efficiency with the environmental impact of replacing hardware. New processors often complete workloads faster, consume less electricity, and reduce cooling demands, making upgrades attractive for large computing environments. However, every replacement also requires manufacturing new equipment, extracting raw materials, assembling components, transporting products, and managing retired hardware. Replacing functional systems too frequently can shift environmental impacts from daily operations to manufacturing and electronic waste. There is no single solution for every organization. Decisions should consider the complete life cycle of the equipment, including efficiency gains, remaining useful life, upgrade possibilities, and opportunities to reuse existing hardware. The goal is to upgrade when meaningful benefits exist while extending the life of functional systems whenever practical. Keeping AI hardware in service longer is one of the most effective ways to reduce unnecessary electronic waste. Servers, processors, and GPUs require significant resources to manufacture, making it valuable to maximize their productive lifespan. Routine maintenance helps improve reliability. Monitoring temperatures, maintaining cooling systems, replacing worn components, and addressing problems early can reduce failures and keep systems operating efficiently for longer. Targeted upgrades also extend equipment life. Increasing memory, improving storage, upgrading networking, or enhancing cooling may improve performance without replacing entire servers. Hardware that no longer supports advanced AI training may still perform well in testing, software development, internal analytics, or smaller machine learning projects. Rather than replacing equipment simply because newer technology exists, organizations should evaluate whether existing systems can continue providing meaningful value. AI hardware often remains useful even after leaving high-performance production environments. Older processors and GPUs may no longer support the largest AI models, but they can still perform valuable work in many other settings. Educational institutions can use retired hardware to teach machine learning, programming, and high-performance computing. Research organizations may benefit from equipment suitable for simulations, experiments, and smaller AI projects, while nonprofit organizations and smaller businesses can gain affordable access to advanced computing resources. Reuse extends hardware lifespan, delays electronic waste generation, and maximizes the value of existing manufacturing resources. However, organizations should also evaluate energy efficiency, maintenance requirements, compatibility, and overall practicality before assigning equipment to new roles. When secondary use is no longer realistic, responsible recycling becomes the appropriate next step. Responsible AI hardware management begins long before equipment is retired. Planning for upgrades, repairs, reuse, and eventual retirement helps organizations make better long-term decisions while reducing unnecessary waste. Maintaining accurate asset inventories is essential. Information about hardware age, configuration, condition, maintenance history, and current use helps identify opportunities to extend equipment life, reassign systems, or recover valuable components. Organizations should evaluate more than performance when considering upgrades. Remaining lifespan, energy efficiency, maintenance costs, software compatibility, and secondary uses all influence whether replacement is truly necessary. Every asset should have a defined path. Whether it remains in service, moves to another workload, is repaired, repurposed, used for parts, or responsibly recycled once its useful life has ended. Hardware designed for modular upgrades and easier repairs can significantly improve long-term sustainability. Instead of replacing complete systems, organizations can update processors, memory, storage, or networking components individually while keeping the rest of the infrastructure in service. Repairability is equally valuable. Accessible replacement parts, technical documentation, and serviceable designs allow equipment to return to operation after relatively minor failures, reducing unnecessary hardware retirement. Software support also influences hardware lifespan. Systems that remain compatible with modern applications can continue serving useful roles in education, development, testing, or smaller AI workloads, even after leaving high-performance production environments. Future AI infrastructure should combine performance with adaptability, allowing technology to evolve through upgrades and repairs rather than complete replacement whenever possible. Shared computing allows organizations to access powerful AI resources without building their own large computing environments. Cloud platforms enable businesses, researchers, and institutions to use advanced hardware only when needed, reducing the need for duplicate infrastructure. Higher hardware utilization also improves sustainability. Instead of sitting idle, shared servers and processors support multiple workloads, helping organizations gain more value from equipment that has already been manufactured and deployed. However, shared computing does not eliminate hardware lifecycle challenges. Cloud data centers still depend on processors, servers, storage, networking equipment, power systems, and cooling infrastructure that will eventually require upgrades and replacement. For this reason, cloud providers also benefit from strong lifecycle planning. Reassigning equipment, extending hardware life, repairing components, and responsibly recycling end-of-life systems all contribute to more sustainable AI infrastructure. Sustainability should be part of AI infrastructure planning from the very beginning. While performance, cost, and energy efficiency remain important, organizations should also consider how long equipment will remain useful and how easily it can be upgraded or repaired. Questions about future software support, modular design, replacement parts, and secondary uses help organizations make better long-term decisions. Hardware that remains compatible with modern software can continue serving valuable roles even after leaving high-performance environments. Flexible system designs also reduce waste. Instead of replacing complete servers, organizations can upgrade specific components that limit performance while preserving the rest of the infrastructure. The strongest AI strategy balances computing performance with durability, repairability, upgradability, resource efficiency, and responsible end-of-life management. Artificial intelligence will continue advancing, bringing larger models, faster processors, and more powerful computing systems. The challenge is ensuring that this progress does not create unnecessary electronic waste. Organizations can support both innovation and sustainability by maintaining equipment carefully, upgrading individual components when practical, repairing systems, and assigning older hardware to workloads that match its remaining capabilities. These practices help extend hardware life while reducing unnecessary replacement. Responsible retirement is equally important. Before equipment leaves service, organizations should evaluate its condition, protect sensitive information, identify opportunities for reuse or repurposing, and separate hardware that has reached the end of its useful life. AI depends on physical infrastructure, and managing that infrastructure responsibly is essential. Sustainable progress means advancing technology while making thoughtful decisions throughout the entire hardware life cycle. Artificial intelligence continues transforming industries, but every breakthrough depends on physical computing hardware. Processors, GPUs, servers, and supporting infrastructure all require careful management from installation through retirement. A responsible approach begins by using existing equipment efficiently, maintaining systems, upgrading individual components when appropriate, extending hardware life, and repurposing functional technology whenever practical. When AI hardware has reached the end of its useful life, responsible recycling provides the final step in sustainable lifecycle management. EACR helps organizations manage retired AI training hardware, servers, processors, GPUs, computers, and other end-of-life electronics through responsible recycling solutions. By planning upgrades carefully, extending equipment life, and recycling responsibly, organizations can support continued AI innovation while reducing environmental impact.